Okay, so now let's start section 3.7, the implicit differentiation. So in the previous six sections, 3.1 to 3.6, we talked about the definition of the derivative and how it's defined right through the limit definition. And then on top of that, we introduced a lot of rules, right? The power rule, right? Constant multiple rule, product rule, quotient rule, and also 3.6, the chain rule, okay? And you see, guys, when we use all these rules to handle the questions here, believe it or not, our fx actually is all defined explicitly, right, in terms of the independent variable like x or t, right? But there will also be some situation that you have a relationship between the x and y, but you cannot rewrite y or solve y in terms of x, okay? So that's at that situation, we're going to use the implicit differentiation, okay? And look at this example here. X cubed plus y cubed plus 6xy equals 0, okay? And you can think about it, x stands for the x coordinate on the two-dimension plane, xy plane, and y stands for the y coordinates, okay? And I actually draw the graph of this equation. You can take a look at it here. It's like this, okay? And in fact, very clearly, excuse me. So very clearly, you can see that actually y is not a function of x. Agree, right? Because we can apply the vertical line test to see it's not a function. Okay. However, do you see that, guys? I don't know. So at this point, do you see it has a slope of the tangent line, right? Or a tangent line, right? So of course it's gonna have a slope. And at this point, it's gonna have a tangent line, and at this point it has tangent line. At this point it has tangent line. Meaning, guys, even y is not a function of x. But you see that when x and y satisfy this equation, it has a corresponding graph, and then at the point on this graph, it will have the corresponding tangent line. And very easily, we might want to know that, okay, what is the slope of that tangent line, okay? So all of these questions we actually can handle with the implicit differentiation, okay? And the implicit differentiation, it's very straightforward, okay? What it does is just do two steps, okay? So step one, you take the derivative with respect to x on both sides, okay? And you treat y is a function of x, even it's not, okay, guys? Just to assume y is a function when we do this. And two, and solve dy dx, okay? So those two steps. Now let me show you with this example, and I think you're gonna understand what's going on there, okay? So let's use the other side. Okay. So here we go. We have x cubed plus y cubed plus 6xy equals 0. Okay, so now I'm starting to do is I want to take the derivative with respect to x on both sides. Okay, of course, guys, d0 dx, do you agree? It's still 0, right? Okay, so now based on the derivative rules, this is what I can write, right? Okay. All right, so the derivative of x cubed, which is gonna be 3x squared, okay? Now here comes to the interesting part, guys. Treat y is a function of x. Okay, treat y as a function of x. And how do we do that? Well, starting from here, guys, and also starting from here, let me use a different marker. You're going to use the idea of chain rule from 3.6 to handle this. Okay. And let me write the result first, which is 3y squared times dy dx. Okay. So where is this from? Now let's use a mimic. Okay. Suppose, guys, I'm having this, something like this. Okay. Let's say I have a function x squared plus 1 cubed, and I'm asking to figure out the derivative of this with respect to x. So following 3.6, the chain rule with the power rule, do you see that the derivative or this, or d of this dx, do you see it equals 3x squared plus 1 squared times the derivative of the inside function, which is 2x, right? We know that. But now, guys, if we make a substitution for the inside function, let's see, set y equals x squared plus 1. And then, do you agree this is what I get? dy cubed dx equals 3y squared times dy dx, which is exactly here. As you can see, guys, for here, this is just one example. Okay, what it means here is this y cube stands for a composite function. Y is a function of x. Okay, I just give you a specific case like this. You know, in fact, your y can be any type of functions with x. Okay, because we just learned this from 3.6. So I think this is an example. This is a specific, this is the general case, okay? Because you treat y as a function of x, okay? And so what we'll do is, right, so we apply the power rule, which is 3 times y squared, and then times dy dx, which is the derivative of the inside function. Do you see that? This actually is exactly using the chain rule. Okay. Now let's move on to this one. Now this part is always a lot of students get a mistake here. d6xy dx. First of all, 6 is a constant. I can write into this, right? Bring the constant out. And also, look at here, guys. Inside, you see it's x times y. So this, even y is a function of x. But the structure of this is d xy dx, and it's x multiplied by y. So for here, when you to do the derivative, what you need to do is to use the product rule, okay? And we have 3x squared here, we have 3y squared dy dx, and we have plus 6. Again, the product rule, it says it's dx times y, right? Plus x times dy dx, it equals 0. Okay. So dx equals 1, right? So copy 3x squared plus 3y squared times dy dx plus 6 times y plus x times dy dx, and it equals 0. Okay, and let's see, where's this? You see, if you got to here, I will see that 90% of the work is done. Why? Because we already completed the differentiation with respect to x on both sides. The last step is to reorganize and solve for dy dx. Let's see, how do we do that? Well, I have 3x squared plus 3y squared dy dx, and I multiply this, give me it's 6y plus 6x times dy dx equals 0. Okay. What I can do is I can keep the terms involved with dy dx on the left, which is 3y squared plus 6x dy dx. Okay. And subtract 3x squared, give us negative 3x squared. Subtract 6y on both sides, give us negative 6y. And hence, dy dx equals negative 3x squared minus 6y over 3y squared plus 6x. And mission complete, guys. Okay. So this is dy dx. As you can see that, guys, the result is not only involved with the independent variable x, but also the dependent variable y, right? So this is a problem for the implicit differentiation, okay? And so this is just the first part. And the second part, we're gonna practice more examples, and then, okay, so I'll see you